Hello everyone. So again, welcome back to our latest lecture session. So let's again have a quick recap of what we discussed in the previous session. So we have been looking at a particular scenario of two half reactions. One is Fe3 plus being reduced to Fe2 plus, and C2Cl4 being reduced to C2HCl3, right? And then we looked at various scenarios, as in one scenario as in we considered no other reactions other than complex formation, and which particular half reaction, and then we try to understand, I guess, right, which particular compound which would reduce which compound, and so on. And the second case was we considered a case of redox along with the relevant complex formations, and then we saw that the situation wasn't the same as what we observed in case 1, right? And then now for today, or today's session anyway, so we are going to look at the natural scenario, right, where you would expect obviously complex formation, precipitation or the solid phase being present, and obviously redox reactions going through in conjunction, and then try to understand the system, right. So let's try to look at what where we are. So I believe we were looking at Fe3 plus being reduced to Fe2 plus, right, and also with respect to C2Cl4, right, plus H plus 2 electrons, right, would go to C2HCl3 plus Cl minus, right, and I believe we had P naught values to be 13.03 and 10.84, right. And so we worked out two cases, when one was we had no other reactions, only the redox, and we saw that P value came out to be 13.03 and P2 came out to be 8.84, and because P1 greater than P2, right. So what would have been the what is it now, overall reaction? It would have been swapping this C2HCl3 plus Cl minus, because 2 electrons I will need to multiply that, so I will do that later, I guess, right, going to C2Cl4 plus H plus, right, and here if I multiply this by 2 plus 2 Fe3 plus, right, going to 2 Fe2 plus, right. So here if there were no other reactions present, this would have been the overall reaction, or C2HCl3 would have reduced Fe3 plus to Fe2 plus, and this is what you would have observed. But we saw that when we considered the other particular case, when we also have complex formation along with the redox, we saw that the P1 dropped to I think 4.9 and P2 would still be the same, right, 8.84 or 8.84, right. And so now P2 is greater than P1. So thus the overall reaction would be 2 times Fe2 plus, right, is going to 2 times Fe3 plus, right, while reducing C2Cl4, right, to C2HCl3, right. So obviously in this case ferrous iron can reductively dechlorinate, so we are dechlorinating, right, that is what you see here, and by reducing the oxidation state of carbon, that is what you see. So it is reductive dechlorination of PCE here, right, the tetrachloro or perchloroethylene. And why is that again? Because now unlike the other case when we had P1 greater than P2, we now have P2 greater than P1, right. So you see that when we considered complex formation, which is what you would observe out there, the scenario changed. So obviously now we are going to consider the aspect wherein we have complex formation, precipitation or the relevant solid phase being present, right, and also the redox obviously, I guess. So let us see how the situation changes now, right. So for this obviously again we need to come up with our total component balance with respect to Fe3 plus, right, and for this again let us try to see how to work it out by hand and then by Vimitech to be able to understand the relevant basics and also to be able to understand the relevant software, right. So here we are going to have a new phase, right. So for that I am going to list the relevant species. So, here I am going to again assume that Fe2 plus does not form any complexes or does not precipitate, which is not a bad assumption, right, and that is why I have only Fe2 plus here, but we know Fe3 plus will have the complexes, right, FeOH 2 plus, FeOH twice plus, and FeOH thrice neutral charge, and FeOH 4 negative charge, and obviously the solid phase FeOH thrice the solid, right. So, obviously here we need to look at the relevant component balance with respect to Fe total. So, if I can write that down, I guess Fe3 plus total would now be equal to, based on what we worked in our particular aqueous complex based example, I am going to write that down directly here, right. It is going to be equal to Fe3 plus into 1 plus beta 1 star by H plus concentration, which we know in this case because we assumed that the pH, or we are considering the case when pH is equal to 7, right, plus beta 2 star by H plus square plus beta 3 star by H plus cube, right, plus beta 4 star for divided by H plus to the power of 4, and obviously we need to consider the other unknown, which is your concentration of the solid that has precipitated out, right. This again is your unknown here. So, again keep in mind here to again refresh your memory, the Fe total, Fe3 plus total would be the sum of Fe3 plus in the aqueous phase plus the Fe3 plus in the solid phase, right. So, this obviously is the aqueous phase and this obviously is the solid phase, right. So, here though, unlike the previous case with respect to the complex formation only, where by knowing the pH to be 7 we could have solved for Fe3 plus concentration, the free metal, we can't do that because we have this second unknown, which is our concentration of the solid or the amount of solid that has precipitated out from the solution per that unit volume of the solution, right. So, again keep in mind, again to refresh your memories, in general when we look at activities of the solids, we say they are relatively they are 1 in that case when the solid is a pure solid, right. But here to be able to solve the system, we are coming up with this value, or this variable, this concentration of the solid, which is equal to the amount of solid that has precipitated out from the solution per unit volume of the solution. So, that is this particular variable, right, and we need to be able to solve that. So, how do we solve that by hand now? So, here I have two variables and only one equation. So, how do I get that done? So, obviously we need to look at the relevant what do we say precipitation and dissolution based equations. FeOH thrice the solid will be in equilibrium with Fe3 plus 3 OH minus, right. So, from this again I will have my solubility product to be equal to Fe3 plus activity times activity of OH minus to the power of 3 by activity of the solid, which will be equal to 1, right. So, from this particular background with respect to our precipitation and dissolution, we have the relevant solubility products or the solubility constant, and with this we now have our second equation. So, this is our second equation, right, and we still have Fe3 plus. We know what the value of OH minus is because the pH we are assuming to be 7, right. So, the only unknown here is Fe3 plus, right, and here we have Fe3 plus and what is it here please, FeOH thrice the solid, right. So, from here I can calculate the what do we say, so I have an additional unknown, right. So, from here I can plug this particular value here, right, or substitute for the relevant value of Fe3 plus and calculate FeOH thrice solid and get the relevant aqueous phase concentration of Fe3 plus or obviously the Fe3 plus metal free metal concentration, right. So, obviously we need to go ahead and look at those relevant aspects in such a manner, yes. So, again this is how I would obviously work it out by hand. So, once I do that, obviously I am now going to have Pe is equal to Pe naught minus 1 by n, which is 1 electron transfer, right, log activity of Fe2 plus by activity of Fe3 plus, right. So in effect, what would this lead to now, right? What would it lead to? We are assuming that Fe2 plus has or forms no complexes or doesn't precipitate out, right, which is a decent assumption. And we know that Fe3 plus will form a lot of complexes, which we looked at in the previous session. And we also know that it can precipitate out, right? So the Fe3 plus concentration is going to be now much lower. So in effect, what does it mean? It means that the value of Pe is going to fall further, right? So let's see how to understand this system in vMinTech, I guess, right? So let's switch over there. So with respect to vMinTech, I'm going to assume that I have FeSO4 not at 10 power minus 3 concentration, right? And also FeCl3 at 10 power minus 3 concentration, right? Meaning Fe2 plus total would have been equal to 10 power minus 3 and SO4 total, right, would be equal to 10 power minus 3. And again similarly here Fe3 plus total would be equal to 10 power minus 3 and Cl minus total would be equal to 3 into 10 power minus 3, right. So now I am going to plug these values in and try to calculate what it is that I am going to expect in the what do we say scenario or out there in the nature when I also assume that the relevant solid phase is present, right. So I am going to go over here to vMinTech and plug the relevant components in. So let me first plug in the metals Fe3 plus and 2 plus, and so it's 1 millimolal. I am going to plug that in, add that to the list, and Fe3 plus, right, again same concentration, I am going to add that to the list, and SO4 2 minus 2 is at the same concentration, right, and where is SO4 2 minus, okay, it's right here, and that again add to the list. Cl minus though at 3 millimolal, so let's look at where that is, and Cl minus is at 3 millimolal, right. So I'm going to have that added to the list, and I know that the pH we are fixing it at 7, right. Let's view or edit the list here once, 2 plus, 3 plus, SO4 2 minus and Cl minus total, that's fine here. And obviously here the aspect is that if we try to solve for the system right now, it would not consider the precipitation, right. So I obviously need to specify that precipitation is possible, and also I need to specify which particular solid is the most probable or the predominant or the controlling solid. Again, what is this concept of controlling solid? So if I can again refresh your memory, right. So we know that different solid phases are possible, right, but at a particular given time you will have one particular solid that we consider as the controlling solid. And why is that? Because let's say in our particular equation that we looked at here, K solubility product here, right, for different solids we would obviously have different solubility products, and that would lead to different Fe3 plus concentrations in equilibrium at that particular scenario, right, for that particular controlling solids. So if you do not identify the controlling solid well enough, right, you can end up erroneously calculating your or end up with erroneous calculations with respect to your free metal here, right. So again here we are going to, let's say, assume it's the amorphous form, the most soluble form. So solid phases, specify possible solid phases, right. So limit to those solids possible based on the components that have been defined. So I'm going to go with the amorphous form here, right, ferrihydrite, let's say, right, and I'm going to add that to the list. And with respect to FeOH, you wouldn't assume any what do we say solid to be formed in general, so I'm going to let that be. So I'm going to go back to the main menu. So now I specified that a particular form of FeOH thrice can precipitate out, right, ferrihydrite, right, and now we also obviously need to ask the system to be able to calculate the PE and EH, specify PE and EH. So we know that we need to compute PE, and here it asks us to supply a guess. So earlier the value when we just considered aqueous complexes was 4.9. Now it's going to fall further. Let's say I'm going to say be equal to 1. Let's say the PE guess that I'm going to give is going to be equal to 1. So save and back to main menu. So right now we have given all the components, right. all the components, yes, and this is the dummy with respect to the electrons, I guess, because it's a redox couple here. Okay, that's something we haven't done yet, I guess, specify redox couples. So Fe2 plus and Fe3 plus, that's something obviously we should have done, right? And back to main menu, right? Okay. So now everything seems in order. So we specified the relevant components. A2 itself will calculate for the complexes, and we specified for the relevant solid phase for Fe3 plus, let's say, assuming it's the amorphous form, more soluble form, right? And then we also specified for the redox couple, and now we are going to ask the vMinTech to run for the system, right? Or before we do so, let's try to understand the system. Back to list of fixed species, let's say. So I'll say for now I'll delete the species, we are going to come back to that again, and without the redox couple, let's try to understand the system here. Okay, so I guess let me restart that because I removed vMinTech or the relevant aspect there. There seems to have been a minor error. Let's redo that. So I'm going to fix the pH at 7. So I'm going to go with Fe2 plus as 10 power minus 3 again, right? Add that to the list. Fe3 plus 2 at the same concentration, and SO4 2 minus at the same concentration, Cl minus at 3 millimolal, at 3 millimolal, right, because we are having FeCl3, right, add to the list, right, pH 7 millimolal, view edit list, and seems fine for now. Specify solid phases, specify possible solid phases, right, limit to that list, and I am assuming ferrihydrite can be formed, right, and we are going to add that to the list, and back to main menu and run MinTech, and now we have the relevant values. So before we go further, let's look at the species distribution. We see that 89% of the total Fe2 plus is present as Fe2 plus the free metal, and with respect to Fe3 plus, you see that the free metal is nowhere in the picture, yes, and let's say go back to the main output menu and then look at the Fe3 plus concentration. Now it's 3.15 into 10 power minus 18. Let's plug that in here, try to understand that. So now we have Fe2 plus to be 8.9 into 10 power minus 4, and Fe3 plus to be something around 3.2 into 10 power minus 18, right. This is of the free metal, obviously, 10 power minus 18, but how much did we plug in? The total was Fe3 plus total was 10 power minus 3, and here Fe2 plus total we plugged in was 10 power minus 3 2. So you see that more or less thus free metal concentration is more or less similar to what we plugged in with respect to Fe2 plus, but with respect to Fe3 plus, when we consider the solid phase, right, when we consider the solid phase and complexes, we see that it's much lower, and to I think when we considered only the complex phase, it was something around the activity of Fe3 plus was something around 10 power minus 11, right. So now you see when we consider the solid phase and the complexes, the concentration of the free metal Fe3 plus is much lower, right. So obviously what would you expect if I plug in these values of Fe2 plus and Fe3 plus in my PE equation? You would expect that the PE value would fall further, right. So this is the most realistic scenario. Let's see that with respect to our vMinTech here. Let's try to calculate that. So I'm going to say specify the redox couple, right, and that's going to be Fe3 plus 2 plus. So it says fixed, but I need to specify that. So back to main menu, parameters, specify P and EH. I'm going to ask it to calculate. So I'm going to have to give a guess for my particular case of PE, right. So because I know it's going to be lower, I'm going to go with 1, right. Save and back to main menu and run MinTech. And now you see that the P value is remarkably low, minus 1.584, right. So now you see that the PV value, right, for P1 is minus 1.584, right, and the P2 value for C2HCl3 to C2Cl4 to C2HCl3 is still going to be equal to 8.84, right. and now you see that the PE2 value is far greater than PE1, right. Again, what does this mean now? In this particular case, there is a very strong tendency for your ferrous iron to be to want to reduce C2Cl4, right. So let's try to summarize what we have been up to thus far, I guess, right. So again, we now see that PE1 is much lesser than PE2, right. But what was the case when we only considered that there were only redox reactions and no other reactions, right. We saw that the PE1 I believe was 13.03 and PE2 was 8.84, right. And when we considered complexes, I believe the PE1 was 4.9, PE2 stays the same, right. And here itself we can observe that here PE1 was greater than PE2, right, and here PE2 is greater than PE1, right. And when we consider the case of the complexes and the solid phase, right, and redox, obviously we saw that the PE1 value is now much lower, and I think we end up with a value of minus 1.8, okay, minus 1.58, right, and PE2 is still going to be equal to 8.84. So PE2 is much greater than PE1, or PE1 is much less than PE2. So again, what does this mean? That ferrous iron would very much strongly want to reduce, let us say, your particular chlorinated solvent, which is C2Cl4, right. So here I guess you see the role that the relevant aspects or the relevant chemical process play here, right. So redox, you want to know, let us say, which species are present or the relevant redox couples, but to be able to understand the relevant concentrations of the redox couples, right, in the solution, what do you need to know? You need to know, let us say, what are the relevant aspects, other chemical process that can influence these particular compounds, right. So from your particular background with respect to the 4 major chemical process we have considered, right, we saw that, let us say, Fe2 plus and Fe3 plus, right, they can form complexes. We worked out the relevant scenario, and then we saw that from our background we know that again solid phases can be formed, and then the relevant what do we say, PE values were calculated. So and you see that in each case you see that Fe3 plus concentration keeps decreasing with each case, right, and thus obviously the PE value too keeps decreasing. So you see that Fe without complexes, right, you would have seen that C2HCl3 would have what do we say, reduced Fe3 plus, right. But now you know, let us say, considering what you would expect out there in the nature, right, with respect to the solid and the complexes, and again keep in mind that the solid phase that we assumed was the most soluble form of the ferric iron that we looked at, right. Obviously the scenario will change if I looked at the or consider the more insoluble forms. Let us look at that later, but let us try to understand the system. So when I consider this case of what I would actually expect out there, I see that Fe3 plus concentration is remarkably less, meaning the PE1 value for the relevant Fe3 plus going to Fe2 plus or Fe3 plus being reduced to Fe2 plus is much lower, meaning in that case, right, Fe2 plus would act as a strong reducing agent, right. The PE value is negative there, right, or PE minus P naught is going to be relatively low, right. So strong reducing what do we say, Fe2 plus would want to obviously reduce the relevant compound, right, and be oxidized to Fe3 plus. So let us write down what it is that I would have expected. So relevant half reactions were Fe3 plus electrons goes to Fe2 plus, right, and we also had C2Cl4 plus H plus, I think it is hydrolysis, right, 2 electrons goes to C2HCl3 plus Cl minus, right. So because PE2 is far greater than PE1, what does that mean? Fe2 plus, right, is going to be oxidized to Fe3 plus. So what does that mean again? Fe2 plus is going to reduce C2Cl4, right. So Fe2 plus to balance out the electrons, I guess, 2 Fe2 plus, right, 2 Fe3 plus, and what does it try to do? It wants to reductively dechlorinate, right. So this is what you would observe, I guess, right. and the system strongly favors this particular reaction to go from or proceed from left to right, right? And this is what obviously we have been able to look at. So I guess the last aspect we are going to consider before I wrap up today's session is with respect to solid phase, I believe we considered ferrihydrite, right? The more soluble form of your particular case, which is for Fe3 plus, right? So, but let us say if I consider the other insoluble forms or more insoluble forms, how would it affect the system? As in, let us say initially you know that the most soluble form of the solid will be precipitating out first, and then as you have agglomeration and ripening, you know that you are going to have the more insoluble forms formed later on. So, how would the system change, let us say with respect to P or the redox values if the system were allowed to proceed further, let us see. So, in that case, let us say I will say solid phases, specify solid phases, and instead of ferrihydrite, let us say I have the aged one, right, and list of possible, back to main menu, right, and run MinTech, and now you see obviously the P value has fallen further. Why is that? So, instead of just ferrihydrite, I let the system know that both the ferrihydrite aged form, right, let us say probably the crystalline form probably, and also the the ferrihydrite probably the amorphous form probably again, right, are what we say possible solids. So, obviously the more insoluble solid would be the one that the system takes to be at equilibrium, right, if I give you enough time. So, when the more insoluble form, which is the ferrihydrite aged form, right, is present, obviously what does that mean? The Fe3 plus concentration is now going to be much lower. Maybe let us look at that. Okay. So, it is now 10 power minus 19, one order of magnitude lesser than what it was earlier when we considered just ferrihydrite. So, obviously what did that translate into? That the P value is now much lower than 1.5 or something that we observed earlier. So, what would happen if I looked at the more insoluble forms? Let us see. Let me delete these two, back to main menu, specify possible solid phases, and I think magnetite is one of the more insoluble forms. So, I am going to have magnetite, list of possible species, okay, that is magnetite, I added that, main menu, and I run MinTech now, let us see, right. So, obviously you now see the P value is much lower, minus 8.048. So, that means again obviously because Fe3 plus is much lower, or the free metal concentration, right, Fe3 plus is much lower, which is 10 power minus 25. And again, why is that? Because the solid phase concentration, pardon me, the solid phase is remarkably insoluble here compared to the other solid phases that we have considered earlier, which were I guess ferrihydrite and ferrihydrite the aged form, right. And thus more insoluble forms means lesser concentrations of Fe3 plus, meaning obviously again your P value is going to drop further, as in the system is going to want to strongly favor the reaction of Fe2 plus reductively dechlorinating C2Cl4, right. So, I guess with the last couple, or I guess the 3 sessions, the system should be clear with respect to why we had to look at all the relevant aspects as in the relevant chemical process, and how there is an interplay between each of these processes, right. So, again I guess we are now going to move on to a few more aspects in our particular redox process later on, right, with respect to the electrochemical cell or such, and also set up the equations by hand for being able to calculate PE. For example, here we are asking MinTech to be able to estimate the equilibrium PE, right. How would you or how can you calculate by hand? We will not go into that in great detail, we will only look at that, have a generic overview, because again this for PE, it is negative log activity of electron, that is a hypothetical what do we say compound, right, that would exist at equilibrium. So, there are some issues there, but we are going to have a generic overview about how to be able to solve that, and then we are going to look at trying to understand the electrochemical cell and so on. So, I guess with that I will end today's session, and thank you.